Here are the three possible rhombi that fit the category of night shapes. We'll see that they are the simplest and can be used as building blocks to make many, but not all, of the more complex shapes.
I'm Miguel de Aguero, coming to you from Sullivan, Missouri. This is chapter 2 of my series of describing the knight shapes, which are polygons inspired by the knight's move in chess. Along with my polka dot whiteboard, I'll demonstrate with these cardboard tiles. We'll talk about their internal symmetries, what compound shapes we can make with them, and their relationship to a rather little-known class of polygons called zonogons.
Before we get to the rhombi, I'd like to ask a question. When looking for the simplest knight shape, can we draw a triangle that follows our rules? Let's give it a try. Let's look at all the possible two-sided combinations and see what it would take to make a closed triangle with a third side. The possibilities are pretty limited, only 6. Can any of these be closed into a triangle with a legal side? No. So triangles are out of the knight shape club. The obvious next step is to look at 4 sides. It happens that if we take any of these 6 side pairs, copy them, rotate them 180 degrees, and join them, we get a 4-sided shape. When we do this to all 6, we get 6 rhombi. But if we eliminate duplications, we narrow it down to 3 different polygons. We can also think of a rhombus from a vector point of view. In each of the 3 cases, we can label the first side V1, the second side V2. The third side is V1 in the opposite direction, negative V1, and the fourth side is negative V2. Adding these together, we get V1 plus V2 plus negative V1 plus negative V2 equals 0, which is another way of saying we end up where we begin. And it turns out that if we try to make a 4-sided figure without using this equation, the perimeter won't close because the route won't add up to 0. It also means that any knight shape, no matter how complicated, can be represented by a similar zero-sum expression. But I'm getting ahead of myself. These 3 shapes are the subject of this video. What is a rhombus? It's a 4-sided polygon with equal sides, but not necessarily equal angles, so they fit into the equilateral polygon category. Here's a cardboard loop that we can use as a model for any rhombus, including these 3. It can be flexed into any angle configuration. Notice that any pairs of adjacent interior angles total 180 degrees. As one corner gets closer and closer to 0, the other corner approaches 180 degrees. That's just a property that all rhombi have. One of the rules for knight shapes is that their vertices have to land on grid intersections. The 3 we've drawn are legal, but are there other ways to draw them that are also legal? After a little playing around, it turns out that each of them have 2 orientations that do land on grid intersections based on their internal symmetry. When I say a little playing around, it's another way of saying I'm too lazy to find a solid proof that it's true, but take my word for it. Remember, I'm an artist, not a mathematician. If any mathematicians out there want to drop a proof in the comments, please do. It's helpful at this point to label these 3 shapes. A is the one that looks like a square, since it is a square. As squares do, rotating it in 90-degree steps always leaves it unaffected. But since it's twisted to match the grid, reflecting it horizontally or vertically reverses the twist. And reflecting it by a 45-degree axis also reverses it. So, two versions. Next we look at B. It's longer and narrower than a square. Rotating this in 90-degree steps changes it, then brings it back to the first orientation. So each time the change in orientation is equivalent to reflecting it by a 45-degree axis. On the other hand, if we reflect it using a vertical or horizontal axis, it's unchanged. The third shape, C, is the longest and narrowest of the three. It acts the same as B under rotation, alternating between an uphill and downhill direction. Under reflection, though, C alternates orientation by the vertical, horizontal axes and is unchanged by flips across 45-degree axes. What if we rotate any of these shapes by some other angle, like 30 or 55 degrees? The result knocks the shape out of the gridlocked state. And that also goes for reflections by axes other than vertical, horizontal, or 45 degrees. Reflecting them by a 20-degree axis knocks the shape out. Here are some examples of compound shapes that we can make just by joining A, B, and C together along one or more sides. Since the building blocks are gridlocked, any compound shape will be as well. Let's use A and B to try out all the ways they can join. We know that each of the three rhombi have two orientations. It would help if we labeled them differently, so we'll use A and A prime and B and B prime. It looks like we have two ways that each pair can be joined. Running through all of them, we have a total of 8 variations. But they are really just rotations and reflections of the same single shape. We can call this the AB shape. And it turns out that the other pairs, AC and BC, are single shapes that represent all possible ways to join them as well. Rather than cataloging all the sets of 3, 4, 5, etc., let's jump into deconstructing a more complex shape. I have an unlimited pile of rhombi to piece together. One note, there is often more than one way to fill in these boundaries. But if that's the case, any variations will still use the same collection of each shape. In this example, let's tally up the tiles. We used 11 of the A tiles, 9 of the B tiles, and 8 of the C tiles. If we fill this shape, regardless of the arrangement, we will need this exact number of each. Are all larger night shapes able to be tiled using only these 3 rhombic tiles? The answer is no. We can separate night shapes into 2 infinite groups, those that can be tiled with the rhombi and those that can't. Here are some examples in the second group. Some of these we can partially fill with ABC tiles, some not at all. Most of the compound shapes we've looked at so far have had some concavity to their perimeters. How many can we make that are fully convex? It turns out that there are only 2 compound night shapes that fit this extra constraint, the hexagon and the octagon. Why not a decagon or more sides? Because there are only 4 vectors and their inverses that fit the rules, and all night-shaped perimeters are made up of these vectors. The rhombi, the hexagon, and the octagon make up the night shapes that are in a special class of polygons called zonogons. What are zonogons? 1, they're polygons that are convex. 2, they have an even number of sides. 3, they have opposite pairs of sides that are equal and parallel. 4, they are centrally symmetric, which in this case means that a 180-degree rotation leaves them unchanged. Zonogons are just the 2-dimensional specific case of the more general class of geometric objects called zonotopes, which exist in n dimensions. The hypercube would be a 4-dimensional example. Today we're just going to stick to 2 dimensions. To get a better idea of what makes zonogons special, let's leave the night shape rules aside for a moment and look at what they can be in a more general setting. I'll pick 5 vectors in a grid. Each one has a different length and slope. If we draw a path connecting them in order, we get half of a zonogon. The other half is just a repetition of them in the same order, but in the negative direction. We already know the path will close because what's the sum of all 10 vectors? 0. The resulting polygon is technically called the Minkowski sum of the 5 vectors. I really encourage you to dig deeper into this mathematics term. One final neat property of zonogons is that they can always be tiled with a set of parallelograms that are defined by each possible pair of the 5 vectors. There is more than one way to do this, but no matter how we arrange the tiles, we form ribbons of stacked parallelograms that bridge across the polygon from one side to its opposite pair, like a hopscotch game.
I hope these ramblings have piqued your interest in the possibilities of exploring the night shapes. You'd think I've exhausted all their cool properties, but actually I'm just getting started. In my next chapter, I'll talk about what happens when we pair up night shapes and build patterns with them. See you then, and take care.